Another thing that will really set you apart as an electrical and computer engineer, even in your first week in the department, is to be able to read resistor color codes. Now, this is something that, honestly, a lot of people never bother to memorize. They just figure, oh, I can always look it up if I need to. But it's so easy. I would recommend and really encourage you to memorize it or be able to recreate it, which is actually sort of what I do. I think about it in my head, and I'm able to recreate it and figure out what any resistor would correspond to. You can see here in Figure 1 examples of a couple of photographs of resistors. These are very, very small devices, and they come in such a wide variety of possible values that it would really be very difficult to read if we printed the number of the resistance on the side. And so very clever electrical and computer engineers came up with this color pattern of stripes to represent what the resistance is. Now, it turns out that the resistor body itself, you can see the one on the left here is beige, the one on the right is blue. The resistor body does correspond to what type of technology is used to construct the resistor, but both types of technology are exactly equivalent for our purposes. So whether it's beige or blue makes really no difference. Most of the resistors that I see are beige, but if I get a blue one, that's no problem. They're really quite similar. So what we find then is that if you want to work out the color code, you want to look at the contents of Figure 2 here. So most resistors are going to have 4 stripes, and that's what I'm showing here at the bottom of this page. You can see that there is a brown, a black, a red, and a gold. Now, the brown and black are going to correspond to the first 2 digits of the number, the coefficient in engineering notation. The third stripe here is going to correspond to the power of 10 that multiplies it, and then the gold stripe is going to correspond to the tolerance. In other words, how close does the manufacturer guarantee that you are to that listed value? You can see up at the top of this figure the color code and the numbers that correspond to the color code. Here's how I remember them. Black and white go on the left and right. So I simply write out the numbers 0 through 9, and I write 0 is black and white is 9. Black and white. You never say white and black. You always say black and white. So it's always easy to remember that black goes on the left and white goes on the right. Also, after you've been using these resistors for a while, you're going to find out that almost every resistor has a black stripe somewhere, and almost no resistors have white stripes. So 0 is a very common number. 9 is a very uncommon number. So black and white. What color is most like black? Well, I guess in my opinion, it's probably brown. Brown is probably most like black. What color is most like white? Gray. So gray goes next to white as 8. Brown goes next to black as 1. Then the remaining colors just simply follow the Roy G. Biv pattern that you probably learned in middle school. So red, orange, yellow, green, blue. There is no indigo because that's something that was invented by middle school teachers. We just go straight from blue into violet, which is just a fancy word for purple. So you can see here that if you can remember black and white, and then you can remember brown and gray, then fill the rest of it in with Roy G. Biv. You're going to get the color code perfect every single time. Now you'll find that if you go online, you'll find that there are all kinds of these mnemonics of like, I don't even want to repeat any of them, so I don't want to get any of them stuck in your head. But there are all kinds of sentences, that you can use to memorize the color code. I don't find those useful at all. I find it useful to remember black and white, brown and gray, and then Roy G. Biv. But of course, whatever tool you can find to help you memorize it is useful for you. I'll just warn you that several of those mnemonics are very unprofessional, and so I would encourage you to, if you use one of those, just keep it strictly to yourself. If you're wondering about that tolerance stripe at the end, that tolerance stripe follows this pattern. Now I have to tell you that other than gold and silver, I've almost never seen any color stripes other than 5% and 10%. So what you need to remember is that generally it's going to be gold and silver, and the gold is 5%. That's a tighter tolerance. That's a better resistor because it's guaranteed to be closer to the listed value. Gold is better than silver. In the Olympics or in the metals market, gold is always going to be better than silver. Now, for the rest of these, honestly, if I saw a resistor that had any of these stripes other than gold and silver, I would have to look it up. I don't have any of the other tolerances memorized other than the 5% for gold and the 10% for silver. You might say, hey, what happens if the resistor has 5 stripes? Well, that just means that the first 3 stripes are there to indicate the coefficient. The 4th stripe is the exponent, and then the 5th stripe will represent the tolerance. So it is possible that you can have a resistor that will specify 3 digits of coefficient, and in which case you're going to need to have a 5-stripe resistor. So black, brown, Roy G. Biv, gray, white. That's the way that I think about it. And let's see what would be the resistance of the beige resistor in figure 2. And in case you happen to be looking at this in black and white, the stripes are brown, black, red, gold. So if I found a resistor that was brown, black, red, gold, I would say brown. Okay, I'm going to remember that brown was next to black. Black was 0, so therefore brown is 1. Or I can scroll back up here and say, oh yeah, brown is definitely 1. So brown is 1, black is 0. So I've got 1, 0. That's my coefficient. And because there are only 4 stripes, I know that there are only 2 of the stripes used for the coefficient. Then the red, that's going to correspond to the exponent, to the power of 10. Scrolling back up here, red, well, that's a 2. So that's going to mean 10 to the second power. So I'm going to have 1, 0 that comes from the brown and black. I'm going to have 10 to the second power, which comes from red. So 1, 0 times 10 to the second power. This is 10 times 100. 10 100 is 1,000. And as an engineer, we represent this as 1 kiloohm. This capital Greek letter omega here represents the units of resistance. We'll talk much more about resistance next time, but for right now, just know that that's the unit. And then the last stripe is gold. That's the better of the two, so therefore it's going to be the 5% tolerance. So to fully specify the resistance, you'd have to say 1 kiloohm plus or minus 5%. So that 1, 0 came from the brown and black stripes, the 2 came from the red stripe, and the 5% came from the gold stripe. And then again, the unit for resistance is ohms, represented by a capital Greek letter omega. If the resistor has 5 stripes, as the second half of figure 2 does, the first 3 indicate the coefficient. So the blue resistor in figure 2, which has color pattern of brown, black, green, brown, 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 black, green is going to correspond to the coefficient. So if I look those up, brown is 1, black is 0, and green is going to be 5. So this is 105 times 10 to the brown. Well, 10 to the brown is 10 to the 1. So this is 105 times 10 to the first power, or 105 times 10, which is 1.05 kiloohms. And then the tolerance stripe here is brown. I just wanted to exercise something other than gold or silver. Brown corresponds to 1%. So this is going to be 1.05 kiloohms plus or minus 1%. If you can read those resistor values, if you can read the resistor color code, or even just with 10 seconds of thinking about it, figure out what the color code should be, you're going to really set yourself apart from other electrical and computer engineers.